Yeah, I think we can just we have to begin anyway. All right, so welcome to week 10 of AI504. This week we're gonna learn about RNN, recurrent neural networks. So recurrent neural network, yeah, and also we're gonna cover sequence to sequence. So this is a bit more, I guess. All these are important. Like people usually don't use RNN anymore because of transformers. But before that, so RNN was the standard backbone model for encoding sequences, including text and other like time series data set as well. But well, ever since transformer, RNN doesn't really it's not really like widely used as before, but it still is a pretty like like robust model. It's just that it's not as scalable as transformer. So we're gonna learn about RNN. And then sequence to sequence, obviously. So that is still used. Like sequence to sequence, the concept of the sequence to sequence itself is still widely used as of these days. And then lastly, we're going to learn about attention. So this is very important. So attention is what led to the development of transformers. So I will say all these are important. Oh, it's faster than okay. So that's good. All right. So recurrent neural network. So handling variable length sequences is the strength of RNN basically. So if you think about image, like image classification is image to label, right? So you have a function, you have a function, and that receives an image, a 128 by 128 image, and then it classifies into maybe like 1,000 different classes, like cat, dog, person, yada yada yada. So in this case, the length of or the size of the input is fixed. It's 128 by 128 by 3 usually. So CNNs, well, before like ResNet and Inception, CNNs were designed to handle only a fixed sized input. If a model was trained for handling 128 by 128 by 3, then it wouldn't be able to handle like 64 by 64 unless you like upscale it to 128 128. But since like I think it was Inception or ResNet that ever since then the CNNs are actually flexible enough to be trained on 128 128 and then handle 256 on inference or 64 on inference. Of course, the performance wouldn't be that good, but still, like it wouldn't give you an error. So anyway, so that's the how usually image to label is handled. Is you assume that the image or the input is fixed, but the sentence to label, you don't know how long the sentence will be. Like you can't train a model. Like for example, you have a text that's like a text. Oops, a text that comes into a model, and then the model has to classify whether it's positive sentence or negative sentence. Negative. It's a sentiment classifier. Then you don't know how long the text will be during the inference in the test phase. You can train your model up to like 128 tokens or 200 tokens or 300 tokens. You can set a limit, but you don't know how long the text will be during the test phase because you don't know how long you don't know like how long sentences the users will bring into the model. So that's the problem. So it's handling variable length in a sequence is the crux of the problem or the spirit behind using RNN. Right. So yeah, as I said, input size is fixed or input size varies by sample. So sometimes it's 3 words, sometimes it's 5 words, sometimes it's 10 words, sometimes it's 12 words. You don't really know. So before using RNN, the go-to method for handling sentences or text was something called bag of words. So this has been used for a very long time. Maybe if you guys are familiar with topic modeling, such as like LDA, linear latent Dirichlet allocation, topic modeling, that kind of work, they all were built based upon bag of words representation of text, right? So it's a classical way to handle variable length sentences. So the thing that you want to do is convert a variable length sentence into a fixed representation. Fixed representation, so that you can use like logistic regression or random forest or support vector machine models that are trained on and trained and tested on fixed size input. So how you do is, what you do with bag of words is, given a sentence, like I give the ball to John, who gave it to Mary. So it's a sentence. Then you just simply count the number of occurrences of each word. So I occurred once, gave occurred twice, the once, vol once, two twice, so on and so forth. So you just count the frequencies of each word, or each unique words, actually. So then, based on that, you can represent a single sentence as a counting vector like this. So you assume that you just know all the vocab in English dictionary. Suppose that you have like 50,000 vocabulary words in your dictionary, and then you can convert any sentence, how long, how short, it could be a whole book, it could be just a sentence. You can basically convert it into a 50,000 dimensional counting vector. So like bowl occurred, actually they should be ones. Bowl occurred once, gave occurred twice, and so on and so forth. Right? So any given text, you can convert it into 50,000 dimensional counting vector. The problem with that is it doesn't respect the order of occurrences. For example, here, this is first sentence. I gave the ball to John, who gave it to Mary. The second one is I gave the ball to Mary, who gave it to John. So it's a different sentence containing different meaning, different semantics. But if you convert it into a counting vector, they become the same thing. It's because you just switch places between John and Mary. So everything else is exactly the same. So if you simply use the counting vector, the result will be the same. So this will be turned into a 50,000 dimensional vector. This will also be turned into a 50,000 dimensional vector, but they will be exactly the same thing. So, it cannot distinguish between two sentences which have different meaning. So that's the problem. It just, different meaning, same representation. So there's obviously a certain limitation to it. So these kinds of bag of words approach were heavily used in classical NLP. And actually, some texts, most of the things here actually are different. No, sorry. So bag of words is kind of a representation that you use to classify documents, or classify sentences into like different classes, different labels, basically. But here, all these are classical NLP that is a bit more like linguistic. So classical NLP, when I say classical NLP, it means that before the era of deep learning, since like 2014, or maybe since BERT, like 2018, or like GPT 2022, like maybe we can go back to 2014 when people started to use RNNs and word2vec and that kind of stuff. Before that, the NLP researchers focused heavily on these stuff, like what like extracting the syntactic information from the sentences or text, extracting semantic information from the text, extracting discourse or pragmatic, like higher level abstract meaning from the sentences. And in order to do so, in order to extract all these different levels of information from a text, from a sentence, or text, basically, they would usually go to applying all these different techniques, like part of speech tagging, whether a given if we have a sentence coming in, what is the part of speech, basically, like whether it's a pronoun, noun, verb, or adjective, or adverb, like the part of speech for each word. And then parsing is like extracting the structure of the sentence. And named entity recognition, what are the named entities in this given sentence? Like what is it's trying to find a person's name, a product name, company name, a geopolitical location, something like that, or name, money, currency, or numbers, that kind of stuff. Semantic role labeling is a little bit more abstract. It's a little bit more semantic. So all these were they all worked in combination. Like you would use all these together on a single piece of text to extract as much information as possible. So, and it seems that they're now all made obsolete by deep learning, especially with the advent of ChatGPT. ChatGPT doesn't do any of this. We don't look for whether, well, we don't classify what kind of part of speech tags each word is, like whether it's a noun or pronoun or adverb or verb or adjective. We don't do that. We don't do any parsing. We don't like ChatGPT can do this automatically. You can just ask, like, given this sentence, what are the part of speech tags in the sentence? You can just ask it and then it'll do it for you. And interestingly, the underlying working mechanism with ChatGPT doesn't involve any of this, which is interesting. It's just that you pour a bunch of text into transformer and just train it, and then that's it. So it seems that they're made obsolete, but who knows? Maybe it'll come back sometime later. They all have their uses, especially like linguistic uses. All right, so now we go to RNN. So recurrent neural network, it's to represent or encode variable length input. We talked about variable length input so far. The vanilla RNNs represent the vanilla RNNs like equation or formula is very simple. It's just that the hidden representation or hidden vector at tth time step is calculated by this. There's a nonlinear activation function, which is originally a tanh, and then you have 3 components. So this is bias. What happens is that this is the input to the model at tth time step. So xt is the input to the model, and it is linearly transformed with a matrix. This is the hidden representation or the hidden vector from the previous time step, t-1, and it is also transformed by a matrix. And you add all these 3 together, you non-linearly transform it, and then that becomes your new memory or new hidden vector. So basically, this is the H is what holds the information that has been given so far to the RNN. So you usually start with H0, which is usually, you start with H0, which is usually set to just 0 vectors, all like 0. And obviously, the size of this hidden vector is up to you. It's a hyperparameter. It could be 128, it could be 64, it could be 200. It's up to you. So you start with a 0 filled vector, and then you put the first input in, and then the second input in, third input in, and every single time you update this hidden vector according to this formula, and that's it. So semantically, it's very straightforward. You just want to accept input at each time step while updating the previous memory or your hidden vector, and then add them up, and then non-linearly transform it, and that becomes your new memory. Very straightforward. It's just doing this for loop. Like you do it if you have like 3 inputs, you call this function 3 times, right? And note that I didn't like specify what this input is. It could be a word, it could be a sensor input from like sensor readings, it could be anything. It could be like a stock prices from like 2 days ago, yesterday, today. It could be anything. It could be any sequence. Doesn't have to be like words, right? So yeah, the important thing is because this U and W, the U is the one that transforms the previous hidden layer, the previous memory. W is the one that transforms the current input. These are used at they are the same weights at each time step used. So the same weights are used each time step. So that is why RNN can handle variable length sequence, because you don't use new weights every single time you input x1, x2, x3. If you did that, then your RNN would only be able to handle like fixed size, very fixed size sequence. But because we're using the same U and same W over and over again, it doesn't matter whether it's 3 tokens long, 5 tokens, or 10 tokens long. You just use the same matrix over and over again, just using the for loop. That is why it can handle variable length sequence. So if you rotate this like 90 degrees this way, then it kind of looks like a multi-layer perceptron. It's just a feed-forward neural network where you start with H0, and then this is your second layer, third layer, fourth layer, like this is your ordinary multi-layer perceptron feed-forward neural network. It's just that, there is input coming in from the side. So every layer, there's input coming in, and this input is a new input. This is X1, X2, X3. So it's like an MLP, multi-layer perceptron, that receives new input from each layer. And in order to accommodate that, we use the same weight, W and U, at each layer. Okay. Yeah, we use the same weights repeatedly. Right. So where do we use what do we use RNN for? Where like what are its applications? So the most straightforward one is sequence level classification or regression. So basically sequence level prediction, which is you have an RNN and then you put a sequence into it. So it could be a sentence, and then you do a sentiment classification given a sentence. Like after you put all these, after you feed all the tokens in your sentence or in your sequence, you do a final one final classification, whether the sentence is positive sentence or negative sentence, or topic classification as well. Like if this text is like sports, celebrity, politics, science, international, like like topic classification as in news classification. So there's one RNN to encode input and one prediction at the end. So that is the sequence level prediction. Second one is token level classification regression, or token level prediction, basically. So there's one RNN to encode input, and there are multiple predictions happening, as many as the number of tokens. So what's happening here is, like, for example, in part of speech tagging, you put all the words, all the tokens in your sentence into your RNN, and for each word, you do a classification, whether this is a pronoun, noun, adjective, adverb, preposition, basically, like it's a multi-class classification for each memory, each hidden vector, one multi-class classification. And it's the same thing with language modeling. Like language modeling is where you try to predict the next word. So every single time you try to predict the next word. So it's a like token level classification. So this is a second application number 2. Application number 3 is many to many, sequence to sequence, so to speak. So there's one RNN to encode input, and there's another RNN to decode output. So there is no limitation to how many predictions you will do for this given sentence, because for example, in translation, the number of tokens from the decoder, so this is English to French, right? So you don't know how many tokens you will see in the French side, because it wouldn't be the same as the English side. Like just because this is like 10 words, there's no guarantee that this will also be 10 words. It could be 12 words, it could be 9 words, it could be 5 words. You don't really know. So it's variable. So that is why you need another RNN as a decoder, because you don't know how long the output sequence would be. So you need like variable handler in both sides, in the encoder side and the decoder side. So that's application number 3, sequence to sequence. Right, so we go to the first one, the sequence level prediction, the first one, this one, and we'll look at what happens if we do it, if we were to use it as a sentiment classification, an NLP task. Let's see what happens. So it's a sentiment classification given a sentence, tell me whether it's positive or negative. So it's a binary classification. And the given sentence is, this movie is as impressive as preschool Christmas play. So on the surface, it looks pretty positive, pretty like, because there's like a word impressive, there's like Christmas, there's like, I guess play is also like, I mean, like all like individually, all these words look okay. Like, so as a whole, it could look positive, but actually it's a sarcastic comment, right? That means that this movie was like premature, or like, it wasn't as good as expected. It's as impressive as like children's play. So it's like not good. So it's not a very straightforward task. You have to actually understand this sentence to classify this as a negative sentiment. So how do we do this with RNN? So what happens here is that we're representing each word as a one-hot vector. So we're not using word2vec or anything. We're not using like lookup embedding here. It's just very straightforward. Each X is a one-hot embedding, and we're supposing that there's like 1 million elements. It could be 1 million, but it depends on how large your vocabulary is. If your English dictionary contains 1 million elements, then this will be a 1 million dimensional one-hot vector. If it's 50,000, 50,000 words in your English dictionary, then this will be 50,000 one-hot vector. Basically, it's just a one-hot vector with some size, so as the size will be the same as your vocab. And each dimension represents some word, and in this case, I guess the fourth word, it represents this. So since we're starting with this, we turn on this dimension, and all the others are zeroed out. So here, and there's actually a hidden H0 H0 here, which is the same as 0. But if you add 0, if you add 0, it's just 0, right? So we just don't put it here. So we don't put it here. So what happens is you represent your first input as one hot vector, and then according to this formula, you just simply plug it in. So x1 and wi. So you can assume that this is hidden, or this is not necessary. And the sigma is the tan h. You can assume this is tan h. Next time you put x2, which is the movie, the word movie, and this will be a different different one hot vector. Some other place will be turned into 1, and all the others will be 0, so on and so forth. So you do this until the last one, the play, right? So you will have h10 at the end. After you put all the words inside, you will have h10. And note that I have just omitted the bias, right? But there is a bias. So after h10, after the x10, you will have h10 that is derived from this equation. So you can see that h10 has h9 in it, and h9 will have h8 in it, h8 will have h7 in it, and so on and so forth. You'll go all the way back to h1. So it's like recursive. Like you can have a recursive representation of the hidden vectors. So after that, you assume that h10 just knows all the words that has been given so far with order respected. So the good thing about RNN is it has a strong inductive bias that it will accept sequences. It's a sequence handler, right? So you don't have to use, if you're familiar with transformer, for example, it requires you to use positional encoding, right? But in RNN, you don't need anything to indicate the order of words, because you do a for loop and inherently it'll know that the sequence of words that was given to you. So h10 will remember, theoretically it will remember that the most recent one was play, the previous one was Christmas, the previous before that was preschool, before that was it'll somehow understand the order of input because you have running a for loop using this equation. So h10 is basically a sentence representation vector. It's not just a hidden vector, but you can see it as a vector that represents all this information with order involved. So once you have this h10, then you can simply just plug it into a sigmoid classifier. So h10, and then a vector, and then you have a sigmoid, and then you have outcome from 0 to 1. And if it's close to 1, it'll be positive. If close to negative, if it's close to 0, it'll be negative sentence, right? Cool. So hopefully this is all straightforward to you. Any questions so far? It's a very simple architecture. You just call this with plus bias here. You just call this function as many times as the number of input tokens. So you can assume that if you have a very long sequence, then it'll take a long time to actually encode it and then do anything useful like classification or regression. So it's the time complexity is linearly increasing. So that's why like transformer came around, but we'll get to that later. All right, so the next one is so far this was a sequence level prediction. So you have sequence level prediction. Now next one is token level prediction. So token level prediction, the representative examples that I told you was part of speech tagging and language modeling, but we'll go to language modeling this time, since like ChatGPT and all, it's all language models. So what language modeling is historically is to be able to tell how likely your given text is. Like this sentence, this movie is impressive as personal. Like, what is the likelihood or what is the probability of seeing this particular text in all text space, like all text, like text in like English, text of English. Like this space is infinite, right? You can think of any new sentence, any new words, or any new text, any like paragraph, book, or whatever. Like there's a infinite space. There's a space with infinite number of elements where each element is a proper English text. So in this infinite text space, what is the probability of seeing this particular element here? And you would assume that it is very, very small because the space is nearly infinite, you know. So out of a lot of different, you know, piece of text, seeing this exact text would be very, very small. The likelihood will be very small. So, but you can still try to calculate it. And the way people did before, I mean, still like the way people do it or researchers do it is you break this down, you basically factorize it. So probability of seeing this text, you can break it down into word level. So probability of seeing this sequence of words can be factorized into this. So probability of seeing this, probability of seeing movie given this, probability of seeing is given this in movie, probability of seeing play, you know, like so on and so forth. Like there's like, you know, like you basically factorize it, and then so if you multiply this all together, then it is mathematically the same as this guy, right? So you just factorize it. So what we need, so once we have factorized it, all we need is to be able to calculate the likelihood of this text is to have a model that can calculate this. You know, what is the probability of seeing this particular word given all the words before? So, for example, here, this function needs to calculate the probability of seeing play given all the words before play, or all the words before play. And the one before that, the one before that is we need a function that can calculate the likelihood or the probability of seeing Christmas given all the words before that, and you know, so forth and so on and so forth. And if you go to the very front, then it'll be trying to calculate the probability of seeing movie given this, and then obviously this doesn't have any preceding words, so it's just by itself. So all we need is some word that can, some function that can calculate this, and this will be variable length. Variable length. So traditionally, what people did is, because they couldn't find a good model, a good, you know, algorithm to be able to handle this variable length history or variable length condition, they broke it down into unigram or bigram or trigram. So bigram, for example, is you just assume that, you know, the current word only depends on the previous word and not the word before that. So WT minus 2, you just don't consider it. You just consider that, oh, the probability of this current word will only be dependent or only rely on its immediate preceding word. So that's the spirit of bigram. So you break this down into, well, this will be still this, but the probability of movie given this, the probability is given movie only. So you don't, in bigram, you don't actually have this. And also you don't have all of this. You don't have all of this. So this just immediate preceding word. And then trigram, obviously you could assume what happens. Trigram is the current word, you assume that the current word's probability only depends on the previous one and the one before that. So you have WT minus 2, but you don't care about WT minus 3, T minus 4, T minus 5. You just don't care about all of this, right? You don't care about all of this. You just assume, or you make a hard assumption that your word probability will only depend on the previous two words. So in that case, you know, for example, here, you will not care about all of this, but you will care about preschool. So that is the spirit of trigram. So obviously it has limited horizon, because to accurately calculate this, you need this. You need this, because the factorization requires you to have a function like this. But since you made like compromises, it has limited horizon and it's not accurate anymore. But with RNN, theoretically you can do this, because RNN can handle variable length history or variable length horizon. So with RNN, you can have a way more powerful language models, and actually it can. So when you train RNN on a large like corpus of text, it can start to make a lot of, you know, seemingly okay sentences, like how GPT-1 was able to, you know, like generate interesting text on its own. RNN too could do that. Right. So how would you train RNN to behave as a language model? So it's very simple. You have the input is the same. As before, the sentiment classification, but the output is, now you don't wait until H10 and then plug H10 into logistic regression. You don't do that. What you do is instead because you need as many predictions as the number of tokens, which is you try to predict the next token. So given this is as the input, you need to be able to predict the next word, because what you're trying to do is this, right? You're trying to predict the next word, given the history. So given the history, you're trying to predict the next word, movie. And then given this and movie, which is like this. So H2 will be remembering, theoretically, it will remember that the previous words was movie and this. So H2 will remember that. Given that, you're trying to predict the next word, which is. And then given that, you try to predict the next word, next word, next word, next word, next word, and so on and so forth until the very last time. So at some point, you're going to have to end the prediction cycle, which is where you have to predict the end of sentence, EOS. So there's actually EOS hidden here, like this. So EOS is the indicator that you need to stop predicting the next word, and then your sentence is complete. So when you're training language model, you need to have EOS explicitly. So in the ninth time step, X9, when you put Christmas, then hopefully you will predict, or the model will predict the final word, play. And then given play, the model will predict EOS. And then you know that, oh, since you are seeing EOS as an output, you need to stop the for loop cycle, right? So in terms of like loss functions, there will be how many loss functions? There will be 10 loss functions, as opposed to sequential prediction with the sentiment classification. In sentiment classification, you have only one loss function, the binary classification. The binary classification happens only once at the last step, right? So there's only one loss function. But here in language model, there are 10 loss functions because you predict 10 times. You predict 10 times here. So given this H1, what you do is you try to use H1 to turn this into a next word, which is movie. So out of all the words, W will be as wide as, like the entire number of the entire size of vocabulary, 50,000, 10,000, whatever. Out of all the words you want to predict, out of all the words, like out of like a cat, dog, boy, whatever, you want to predict movie. So you want the Y1 hat, the prediction from this time step Y1 hat, to be the same as Y1, which is actually X2, right? So that it will be your loss function. It's a negative log likelihood that you want your current prediction to be the same as the next word. And, obviously Y10 would be EOS. So 10 loss terms for a single sentence, and loss is usually negative log likelihood. Right, so this is the language modeling with RNN. Question, when do you choose to use a unigram model over bigram or trigram model, or vice versa? Or do people usually just directly use trigram instead of this? I don't think people use unigram anywhere because it's just too restrictive, But bigram or trigram, they were heavily used, and I mean not anymore with ChatGPT. Nobody would be interested in bigram or trigram for language modeling purposes. Yeah. But if you think about it, if you want to use bigram for language modeling, then you need if you want to use bigram for language modeling, then you need to learn this probability. You need to learn this probability by going through all the text in your corpus. How many times do you see a dog that is preceded by the? How many times do you see cat that is preceded by all? Like you need to compute the pairwise probability by going through all the sentences in your corpus, and that means that the number of parameters. This is a single parameter, right? It's a single probability. The number of probabilities that you need to learn is square of your vocab size. If your vocab size is like 10,000, then you need to learn the probability. You need to learn 10,000 times 10,000 probabilities because it's bigram. If you go to trigram, then it becomes even longer because now your probability depends on two preceding words. So it's 10,000 times 10,000 times 10,000. So it's like a cube of the size of the vocab. So there's like obviously a trade-off. And as you increase this number of parameters, the training samples for each probability will decrease, and that becomes, it's just like the curse of dimensionality. Question: are there any applications where RNN still dominate over transformer? And actually, that's a good question. If you have a very rather like short sequence size, like smaller than 50, maybe smaller than 100, you know, like below like 50, 100 or 50, like sequence size wise, and you have not a lot of training samples, like if you have only like, I don't know, like a few thousand samples of sequences where each sequence is rather small, like I said, like 30 or 40, then it's probably going to be better. It's like RNN is going to outperform transformer. Oh, I guess Youngjin, thanks for sharing some kind of project, chat RWKV. Not sure what that is. Anyway, just as I said, yeah. If so, the good thing about, we'll talk about this in transformer like next week, but the good thing about transformer is that it doesn't have any assumptions. Like RNNs have assumptions. RNN assume that you're going to give a sequence to the model. So it was designed in that way. But transformer doesn't have any assumptions. So that is why it's more scalable. Like if you have infinite amount of data, then transformer will learn as much as it can from the data. But in RNN, you can only use sequences to train it, and it's not as scalable. So if you have a lot of data, it's better idea to use transform. If you have small amount of data, RNN is going to outperform transform because it has a strong, if you have a small amount of data and that is all text, all sequences, like if you have a small amount of sequence data, then RNN is going to outperform transformer. Just like how, if you have image and small amount of training data, then CNN is going to outperform transformer because CNN was designed to handle images. It has a strong inductive bias, as opposed to transformer, which doesn't have any bias at all. Hopefully that makes sense. And yeah, going to bidirectional RNN. So because RNN is unidirectional, RNN by itself is unidirectional. It only goes like forward. Like you put this movie is as impressive as preschool Christmas play. Like it only goes this way. So some people might think that is a bit restrictive. It only goes forward. So if you go to forward like many times, if the length of the sequence was like 100, for example, then sooner or later, like H99 or H100, it won't remember what happened way back in H1 or H2 because it's lost in this the flood of input tokens. So what people thought is maybe we should have another RNN that goes backward in time. So backward in time meaning you start from play. You first input play first, and then you input Christmas, preschool, as impressive. So if you go that, then you're going backward in time like this. So in this case, S10 will be the one that receives the first one, and S1 will be the one that receives the first. The S10 will be the one that receives the last word in the first place, and S1 will be the one that receives the first word in the last place. So if you use H10 and S1 like this, if you use H10 and S1 and concatenate them, then this guy, H10, will be able to remember important information from the latter half of the sentence or latter half of the sequence. S1 will be able to remember important stuff from the first half, the former half of the sequence. Oh, there was a question? Hyun-min. Is RNN also available for unformal sentences like emoji or slangs? If you can convert emojis into a symbol, like words are just symbols, like dog, cat, they're all symbols, right? You can convert emojis into a symbol. Slangs, you can also convert that into symbols. Then RNNs will be able to handle it. There is no like zero difference between RNN and transformer in terms of what kind of input it can handle. They can just handle any sequence. It could be time series, it could be like stock prices, it could be text, it could be anything. It's just that the way they were designed is different. RNN has a heavy assumption about the sequentiality of the input. Transformer doesn't care what kind of input is given to it. It's just, it just tries to learn the correlation between all tokens in the given text, in the given sequence. So if transformer can handle it, then RNN can handle it. It's just that RNN's capability is a little bit more limited. Right, just as I was saying. So if you use bidirectional RNN, right, bidirectional RNN, then one goes forward and the other goes backward, and then you concatenate H1, H10, the last one, and S1, the first one, from each encoder. You concatenate them, and then you put it through a sigmoid classifier to do a binary classification. Like, is it a positive or negative, right? So that will be the architecture of a bidirectional transformer. Right, so the next one is actually a quiz. I prepared a quiz that is a little bit more friendly towards people who are not so good at chatting, because so far, the quiz was all based on who answers first and then the 10-second window or 5-second window following that. So the next one is a quiz, and the answer, do not put it on a public channel. Give it to me privately using direct message, okay? Just like what we did in the first practice session, in like the very first practice session with NumPy. The next slide will be a quiz, and you're going to read it. Well, actually, I'm going to read it to you, and I'm going to read it to you, and I'm going to give you maybe a minute to answer it, and then your answer, please give it to me privately. If you post it publicly, then that's the end of the quiz, because if anybody can see the correct answer, like if the public chat was the correct answer. Okay, so quiz 1. So what is the number of learnable parameters in this bidirectional RNN? This bidirectional RNN. I'm talking about this, right? So what is number of learnable parameters? So assume that there are 10,000 words in the vocabulary, and RNN input is, just as I said, it's a one-hot word embedding. So there's no lookup table, and both RNN's hidden layer is 200. Both RNN, like forward, backward, is 256 dimensions, and the binary classification is using sigmoid. You're not using softmax, okay? You're using sigmoid, and you should count biases everywhere. As long as there's learnable parameters, there should be bias. So you should think about it before actually giving, because I'm going to count now. I'm going to give you a minute. You should think carefully. I'm talking about not the number of, like, how many like W's there are. I'm talking about actual number of trainable parameters. Give me a definite answer. Don't give me an equation, okay? Use a calculator or whatever. The total number of parameters, okay? Total number of parameters, including the bias. You should be very careful with the bias, okay? Okay, based on the speed, I should give you guys 1 more minute. I said give me a definite answer. Don't give me an equation. Just the numbers. No need for explanation. This is just a quiz. Right. Yeah, I'm starting to see. Okay, I'm going to give you 30 more seconds. You should not forget about the bias. I said explicitly that you should not forget about the bias. What's my name? My name is Edward Choi. All right, I gave you guys 3 minutes. All right. Right, stop. Don't. All right, all the everything from now here, I'm not going to count as an answer. Stop giving me an answer. Unfortunately, there's not a lot of people who actually got correct answer. Interesting. Okay, I thought this would be a very easy answer. It's harder than before. Actually, no, it should be easier than before because before the questions that I asked was that you needed to have some kind of intuition about machine learning. Like so, like why is it harder to train? Why is it easier to train? Like you need to have like a concrete grasp of the like learning itself. But here it's just, you just count the number of parameters in the RNN and then just add them up with biases involved. The answer is somebody got it right. Actually, maybe I shouldn't give you guys the answer now. Don't want to like discourage you guys from taking the quiz because there is another quiz actually. Like, yeah, stop giving me the answer. The time is over. Like I gave you guys like 3 minutes full. All right, maybe I can tell you guys about the answer of the quiz after the class, or maybe by like on class. All right, we got other things to cover, so we actually need to move on. It's already 11:19, and if we want to do another quiz, the next quiz will be actually easier than this one in terms of calculation. You don't need a calculator. Like here, you needed a calculator, right? But here in the next one, you don't need a calculator. So the limitation of RNN has vanishing gradients. So obviously, if you have a long sequence like as I said, H100 will not be able to will not be able to remember H1. So that's why we just use bidirectional RNN, right? Even bidirectional RNN, it's not a perfect solution. And so input from distant past is forgotten. For example, this is one of the challenging tasks that used to be in papers back in like 2016, 17, before like Transform came out. Like Jane walked into a room, John walked into it too. It was late in the Jane. So you need to understand, you need to remember all this all together in order to be able to say this is John. So it has a long term dependency. So how do we remedy this? So there are some couple of tricks before Transformer, a couple of tricks that people used to, like, for example, like initialize the weight matrices to identity matrices, use some other non-linear activation functions. And this also still exists. Exploding gradient also exists. Vanishing gradient, exploding gradient, they both exist. This is a little bit easier to handle because you just need to clip the gradient. But here is this one, not so easy. So then came around in 2014 something called gated recurrent unit, GRU. So this is the one that people still use to this day. So it's either LSTM or gated recurrent unit, GRU. So it has more complex hidden vector computation during recurrence. So before it was just HT equals FWH plus UX plus B, and that was it. But this one, GRU, is a little bit more sophisticated. So the main idea is that you want to keep around memories to capture long distance dependencies and allow error messages to flow at different strengths. So there's a gating mechanism, which the gate is that the gate decides which information goes to the future and which one should be forgotten, basically. So standard RNN looks like this. So instead of W and U, we use WHH, which is a linear transformation for the hidden layer, previous hidden layer, WHX, which is the linear transformation for the current input. And then the GRU uses an update gate and a reset gate. So there's update gate and reset gate. So that uses 2 gates. So the update gate follows this equation. So there's update, we denote update gate as Z, reset gate is R. So there's WZ for the current input, UZ for the previous hidden layer, WR for the current input. WR for the current input, UR for the previous hidden layer. So there is it's very parallel. They look exactly the same. It's just that different. This is WZ UZ. This is WR UR. And note that this one here is sigmoid. So it's not tanh or anything else. It's sigmoid. So it has to be a sigmoid because you want your gate to have a value between 0 and 1. So 1 is like passing the information to the future. 0 is forgetting or resetting the information and not passing it to the future. So it acts as a gate. Like 1 is open and 0 is like closed. So that is why you need sigmoid as a non-linear activation function. So what happens here is that since you have update gate, reset gate, ZT, RT, what happens is that new memory content. So there's H tilde. So it's like an intermediate hidden layer before you get the final hidden layer here. So H tilde is like is something that you have in between. And you calculate H tilde according to this equation here. So what happens is this is W XT, so current input and the previous input. And if you just look at this together, then it's exactly the same as the vanilla RNN. But there's reset unit with a element-wise multiplication or Hadamard product. So if reset gate is 0, close to 0, then this ignores previous memory because this will all go to 0. If RT is close to 0, this term will go to 0, which means that only this term will survive, which means that H tilde will be decided based on the current input only. Only when RT is close to 1, then H tilde will include both XT and HT-1 at the same time. So RT is like a reset gate. So once you have H tilde, what happens is the final one, the final HT, is determined by this kind of like a convex sum, because ZT is 0 to 1. So this term is ZT. This term is -1 minus ZT. So it's like a sum to 1 situation. So HT-1 is the previous hidden layer. H tilde is the one that you calculate just here. So what happens is if ZT, the update gate, is 1, then this term goes to 0, and your new memory is solely determined by, it's actually copy paste, because if Z is 1, then this goes away. This is 1. Only this survives. So HT equals HT-1. So it's just a copy paste from the previous time step. Only when ZT is close to 0, then this term goes away, and this term survives. This term survives. And actually, only this one survives, because if ZT is 0, this is 1, right? So then HT will be solely determined by H tilde. So there's like a trade-off between, like, if RT is like 0.5 and ZT is like 0.3, then there's like different amounts of previous, like, past information, mixing it up with the current information. So that's how, and they're all learned dynamically. Like all these gate values are determined based on these WZ and WR, UR, these values. So they are like, so you have way more learnable parameters than before. Before, it was just this and this, right? It was just this and this. But now you have 1, 2, 3, 4, and 5 and 6 variables. And we all like omitted biases here, right? So it's like 3 times more trainable parameters. But it handles long-term sequences way better than before. So yeah, this is the diagram, what happens. So HT-1 is the previous hidden layer, and the fate of HT is determined by a lot of different factors, XT, RT, ZT, H tilde T, and they all like interplay, and then you get the final HT. So you just need to implement these 4 lines when you're implementing GRU. Like before RNN, it was just 1 line, right? It was just 1 line that looked like this without this, right? But now it's 4 lines, and that's it. So every time you do a for loop, when you go from the previous step to the next step, you just call these 4 lines, and that's it. LSTM is a little bit more complex. It has 1 more gate. So in GRU, you had 2 gates, update gate and reset gate. In LSTM, you have 3 gates. There's input gate, forget gate, output gate. And each gate is calculated in the same manner as before. There's WI, WF, WO. So you have all these gates, and they're all determined by sigmoid, obviously. And then there's like something called C tilde, which is kind of like H tilde, but it's different. So it's new. There's like memory cell, and then the final memory cell, and then there's final hidden state. So it's a little bit more complicated. And the performance-wise, GRU and LSTM, they're very much comparable. They're like mostly the same thing. So if you can use either one, it's up to your preference. I'm not sure about these days, but before in PyTorch and TensorFlow, GRU implementation gave you one output, which is HT. So you give one input, XT, then you get one output. But in LSTM implementation, you have one input. Where's the input? So there you have one input. You get two outputs, CT and HT. So I guess people thought there would be different use cases for CT and HT, but I'm not sure what that is. Question: why is HT minus 1 and tilde HT a trade-off in the update gate? I mean here? Because HT minus 1 is the previous information, and H tilde T is hopefully gets XT, the current one. So, you know, like it's basically just you're controlling the degree of how much you want your current input to be reflected in the final HT. Otherwise, you know, like HT minus, you don't know whether HT minus 1 will actually have previous inputs all reflect. I mean, sorry. If you look at this, the only way XT could flow into HT is through H tilde, right? So if XT is important, it's like a memorable information. If it's a valuable information, then hopefully Z will be close to 0. If not, then hopefully Z will be close to 1 so that you can just forget about it. Hopefully that makes sense to you. Great. All right, now we go to sequence. We have a lot to actually cover. We have the sequence to sequence and attention, so let's speed things up. So sequence to sequence, this is the final application. There were 3 applications. There was sequence level prediction, token level prediction, now it's sequence to sequence. So given variable length input, we want to generate variable length output. So a lot of use cases in machine translation, question answering chatbot, but these days they're now all, you know, absorbed by ChatGPT. And ChatGPT is actually, it doesn't use sequence to sequence. ChatGPT is decoder only. It's a generative model. So we'll get to that next week. So naturally, if we want to do sequence, naturally we need 2 RNNs, as I said, because we don't know how long we don't know we cannot predetermine the size of the output on the decoder side. So for example, here, this is French to English. So there are 4 words in French, and then there are 5 words in English, and you don't know. As I said, just because there are 4 words doesn't mean that there will be 4 words here. So you don't know. So encoder and decoder, they each have a different purpose. Encoder understands French, it accepts French. Decoder generates, outputs English. So they have different purposes. So what is the output of the encoder and what is the input of the decoder? I mean, they still have, you know, like, because RNN has input and output. So you can still imagine what output the encoder will have and what input the decoder will have. Because, I mean, the purpose is that the important thing is that encoder inputs, encoder accepts, and decoder outputs, decoder generates. But there's still like these places are missing, right? So what happens in machine translation is that you need to connect the encoder and decoder so that you can translate, right? If the tie is severed, if there's no connection between the two, then you won't be able, I mean, decoder won't be able to understand what kind of input there was. So it wouldn't be able to generate the corresponding text, right? So you need to connect the two. And the easiest way you can do it is by hooking up H4 to be able to go to S1. So which means that actually there should be, yeah, actually there should be S0 here, and H4 is going to be S0. So what you do is the output from all the other places, they're not used. It's the H4 itself becomes S0. Before I said that H0 is usually initialized as 0 vector, right? So you will assume that the decoder's initial vector S0 would also be initialized 0, but not really. S0 can be initialized to be the same as H4. So H4 becomes S0, and starting from there, you put the start token in. Start token meaning because you have to start somewhere, right? So what you want to predict I am a student, end of sentence, right? So in order to do that, actually, let me just. In order to do that, you need to put start in, and this is kind of like an ignition to the engine. Like start predicting the next word. So the first word should be I, and then the next word should be M, then A student, and US, right? So in order to do that, you need to initialize S0 with H4. So that's how those two are connected. And you can see that when training, the input to the decoder is start I am a student, and the output of the decoder is I am a student, end of sentence. So you can see that this is the same as this, is the same like just like language modeling, right? You need to predict the next word so that you can generate sentences in the inference during the test phase. So yeah, so at training phase, you apply negative log likelihood to the predicted output. So you want y1 had to be the same as x2, this assuming this is x1, and you want y2 had to be the same as x3, and you want y5 had to be the same as EOS. And you do that, you incorporate that in the negative log likelihood function. So the number of n is 5, obviously, here, because there are 5 outputs, 1, 2, 3, 4, 5. So n is 5. So this is the during training. During test, it's a little bit different. So during test, you don't know, you can't put these like the correct answer into the decoder during the test, because you want the model to generate a corresponding sentence, right? So this is given, your French words will be given, and then starting from there, what you do is you start the engine, start the decoder, and see what happens. So hopefully with start given, S1 will output I, and then you plug that I into the S2, and hopefully that'll give you M. Plug that A and M here, it'll give you A, student, and end of sentence, right? So this is hopefully what will happen. Question, so H1, H2, H3 don't have output. Well, I mean, yeah, you don't connect anything out from the H1, H2, H3. They're just there. And H4 doesn't have an output. Actually, H4 itself becomes as 0. So you don't connect anything here, like you don't do softmax or sigmoid. You don't do any of that. They're just there. They're just left there to act as a memory content that remembers the given French words. Right, so that's the end of sequence to sequence, and now we're going to attention. So the attention model came around very early. Actually, it came around in the same year as GRU. So GRU was the first paper ever to use neural networks RNN to do translation without any domain knowledge. Just you have parallel corpus, French, English, and then you dump them into a sequence to sequence RNN models, and then it'll do a translation for you. So that was a very like a groundbreaking paper in retrospect, but obviously it didn't perform as well as those models with like heavy domain knowledge. So, and obviously it's because the GRU itself was not. I mean, GRU is still better than vanilla RNN. So the very first paper, the GRU paper was a translation paper. It was a translation paper, but it wasn't enough. So they came out. So the same group from Yusha Benjo's group, they came up with something called the attention models. So attention model is an addition to the GRU to even further improve the performance of the GRU-based translation model. So the spirit or the core idea is that to use all hidden layers from all time steps to make predictions. So what I mean by that is using all hidden layers. So for example, let's assume that we're doing sentiment classification as before. So it's a sequence level prediction. So this movie is as impressive as preschool Christmas play, right? So before, what we did is we took H10 as a sentence representation vector, and then we plugged that into the sigmoid, and then we did a binary classification, right? But as I said, H10, if it becomes like very long, like H100 or H200, then it wouldn't be able to memorize the previous content, right? And GRU will be able to alleviate that to some extent. Bidirectional RNN will also be able to alleviate that to some extent. But there's another way to do it, which is using all hidden layers. So what I mean by that is, instead of only using H10, we use all HIs from all time steps, and we mix it up. We mix all these up to make a new vector called context vector. So the context vector is a weighted sum of H1, H2, H, like all the way to H10. And the weights, these weights, alpha 1 to alpha 10, they should sum to 1, because you need to put some constraint into it. Otherwise, the magnitude of the C will just explode, because if this is like 10, 20, 500, like 5, then like if you weight sum all them up, then C, the magnitude of the C will be just too large. So it wouldn't work as intended. So you need to actually have a sum to 1 constraint, sum to 1. So this is C, the context vector, is a convex sum of all the H1s to HIs, H1 from H10. And these values, alphas, you don't decide the values. The model will automatically decide the alpha values for you, which is the core idea of attention models. So yeah, once you have the context vector, then you plug that into a sigmoid here, and then you get a binary classification. So this should be way more informed than simply using H10, because now C can see all the H's from all time steps. So you can actively use previous, like past information if necessary. So before we get into how it works, what is it good for? Like, what is good for besides improved performance? I mean, obviously, it'll give you improved performances, right? Because you're using all time step. But the other thing that is good for is it gives you a kind of an interpretation or the explanation of how the model works. Because now C is a combination of all past information. Alphas denote the usefulness from each word. For example, because alpha needs to sum to 1. For example, if alpha 1 is like 0.8 and this is like 0.01, 0.02, like all the way to 0.001, then you know that this model decided that the most important information lied in H1. That's why this is 0.8. So this kind of gives you like indirect interpretation of what the model is doing in terms of attention strength. So yeah. Question: do we train alpha during training, or no? I'm going to talk about how alpha is calculated. I'm going to talk about it now. Yeah. Attention. So here, attention alpha I are generated using an MLP. So there's a separate MLP function that its sole purpose or its role is to calculate alphas for the model. So it's a separate model. So there's RNN. There's RNN that generates H1, H2, H9, H10. There's another model, MLP, feed-forward neural network, that calculates alpha. So let's assume that you have some kind of multi-layer perceptron that looks like this. So there's input, there's hidden layer, then the output is a scalar value. It's a scalar value. It actually should be a dot, not a box. It's a scalar value whose range is -infinity to the positive infinity. So it's just a real value with like infinite range. So I'm going to call this function an A function, y equals ax, and y's range is this. So let's assume that we have an MLP function like this. Then we apply MLP function each time to H1, H2, H9, H10, right? So here the input to this A function, the input to this A function is now the hidden vector of the RNN. So there should be 10 hidden vectors, So 10 inputs. So you have A H1, A H2, A H9, A H10, each generating Y1, Y2, Y9, Y10. And each Y1, Y2 all will have a value between -infinity and positive infinity. So that is not enough, because we want alpha, which sums to 1. All alpha i's sum to 1. We need that. So what we do is take all the y's and put it into a softmax. Then you get alpha I, which is basically a probability distribution, right? So this softmax function ensures alpha i's sum to 1, because y1, y2, all these are -infinity to positive infinity. So you need to normalize them. So you use softmax to normalize them, turn this y1 into alpha 1, turn this y2 into alpha 2, alpha 9, alpha 10. So that is how alphas are calculated. And obviously, this should be trained. These are trainable parameters. These are trainable parameters. So they are trained end to end. You don't train MLP separately. These are trained end to end. Question so far. They are end to end trainable because your C is, well, you can go all the way back to here. Your C is a sum of weighted sum of weight H's, but alphas come into play, and alphas are generated by the A function, right? The A function. So the A function is used every single time the alpha is calculated, which means that and the C will be plugged into a sigmoid. C will be plugged into a sigmoid, right? There should be WC becoming a Y hat, and alpha is generated from Y equals a H1, something like basically. So if you do a backprop from Y1, so there should be of course there should be a loss function that has Y hat. So you start from the back. When you do a backprop from this loss function, it'll go all the way here, here, as well as here. So the parameters from the attention function MLP will also be trained. It'll also get the gradient signal from all the way from the top. So that is why it's end-to-end trainable. Some people get confused that like RNN and MLP are separately trained. That is not true. They're trained end-to-end. And note that this attention function doesn't actually have to be MLP. It could be anything. It's just attention function is just some function that generates a scalar value, and that scalar value generates a scalar value, and the scalar value will be put into the softmax function, and that's it. So attention function could be anything. It could be MLP, it could be CNN, it could be RNN. It doesn't really matter. It's just some function that accepts the hidden layer and then generates a scalar value. Right. So as I said, in the original attention paper, it was developed for translation purposes, but this so far was actually a sentence level, sequence level prediction, not a sequence to sequence. So let's see how attention is used in sequence to sequence setting. So we're doing the same, the French to English translation. And let's assume that right now what we're doing is we're predicting Y2. So we have Y1 in, and then we're trying to predict Y2. So each YI, so you assume so as a recap, each YI is predicted based on SI, obviously, right? S1 gives Y1, S2 gives Y2. So each YI is predicted based on SI. Each SI is derived based on this is derived based on this guy and this guy without attention. So without attention, S2 is the fate of S2 is determined by S1 and Y1, obviously, right? But in attention, it's a little bit different. So each YI, so this is the same. YI is predicted based on SI. This is still the same. The difference is that SI is derived based on 3 things, not 2 things. SI is determined by S1, Y1, and something called C2. So there's another component here. And C2, so CI is derived from S, the previous S, and all the H's. So you should really pay attention to what's happening here. The C2 is the same context vector we talked about in here. It's the same context vector. And this context vector has an index because you need context vectors every single time you predict the next word. Okay? So S2 is determined by S1, Y1, C2, 3 things. And C2 is determined by, you can see the dots here. C2 is determined by S1 and all the H's from the encoder. So far it makes sense? Oh, there was a question from Aldo. When the sequence is very long, over 1,000, 10,000, are we risking vanishing gradients as alpha go to 0? Actually, if you have a sequence as long as like 10,000, 1,000, 10,000, you shouldn't use RNN anymore. But you could. I mean, theoretically you could, and if you do, then the alpha values will be really spread out thin because it has still sum to 1. But if you spread the the total amount 1 to 10,000 different tokens, and like, only very few will survive. And the rest will be all like forgotten. Hopefully that makes sense. Right. So we were saying that the context vector comes into play. So before in the sequence level prediction, the context vector was a weighted sum of H1, H2, H3, H4. That was it before in the sequence level prediction. But here now we're doing sequence to sequence. So now context vector also needs to take into account previous decoder hidden layer, previous decoder memory, so that you can have a more informed context. Because in order to predict the next word properly, you need to understand what you've predicted before your previous input, all the input from the hidden layer, all the input from the encoder, mix them up, and then put them into your next hidden layer, S2, and then predict. So that was the philosophy behind the attention model, attention-based sequence to sequence. So equation-wise, what happens is each yi predict based on si. So this is it. We all know this. Yi is is a softmax prediction based on si only, and each si is derived based on si minus 1, yi minus 1, this guy and this guy, and ci, this guy, right? So the decoder RNN looks like this. So RNN usually has one. So I'm going to go with the vanilla RNN. So vanilla RNN being si equals fw not sh si minus 1 plus u xi plus b, right? So you have two input. Input number 1 is previous hidden layer. Input number 2 is current input. The current input is actually a concatenation of the two. Current input is a concatenation of your previous output, your predicted output, or the current input. This is actually, you can actually write this as x2 because this is the second input. It's just that in translation, you have generative model. You have a generative process. So y1 hat is actually the same as the next input, right? So the input to the decoder is the concatenation of the two, your current input and your current context. So you concatenate them two, and then that goes in here. And the context CI, how it is derived from SI minus 1 and all the H's from the encoder is based on this. It's based on this. So you start with, so context vector is a weighted sum of all the H's from the decoder. But it is also but when it is derived, but it also needs to take into context your SI, right? So what happens is the function, the MLP function, the attention function that we talked about that generates the scalar value, accepts two input, not one input, but two input. Before in y equals ax, we gave it only one input, which was hi, right? But here, this is sequence to sequence. So you have two inputs to the attention function. So the attention function is now f, not a. This is f now, right? So the way you input two inputs is having this equation here. So your previous decoder memory and your current h whatever is mixed by a matrix here. So it's not just a inner product between the two. There's like a convergent. There's like a transformation function w that is a trainable parameter coming between si minus 1 and hj. So you do this basically. So what f does is it calculates, or it tries to estimate the compatibility between this guy and this guy, this guy and this guy, this guy and this guy, and this guy and this guy, and then you will have y1, y2, all the way to y4, and then you put that y's into softmax, and then you get alpha 1, alpha 2, alpha 3, alpha 4, and then that goes into weighted sum of ci, and then that ci is go into the RNN's input as a concatenation, and then you get yi. Doesn't make sense. There was a question. So context vector keeps being updated while decoding. Exactly. There's not just one context vector, because there's C1. If there's C2, it means that there's C1, there's C3, C4, C5, C6, C7, C8. Like every time you predict the next word, you need a new C. All right. Questions so far? Does everybody understand how this works? You're going to implement this in this Thursday. Oh, actually, I'm not sure if you're going to implement attention-based sequence, you're definitely going to practice attention and sequence to sequence. I'm not sure if you're going to practice like this exactly, but but you should definitely keep this in mind. No question? Okay, good. So next one is a quiz. So it's a final quiz actually. So this one will be hopefully way easier because you don't need, as I said, you don't need a calculator. So I'm going to give you maybe 20 seconds for the quiz. So let's see. So the quiz number 2. In the previous translation example, this one. So je suis étudiant US. There's actually I've written it here. Je suis étudiant US. Translating that to I am a student US. This is our example. How many times is the attention function f called or used? That's the question. How many times is it used to finish this, converting this to this? So give me an answer. I'm going to give you 20 seconds. All right, 10 more seconds. 10 more seconds. All right, stop. I think some people are just, like submitting multiple answers, but remember that only your last answer will be counted as a true answer. All right, so I'm going to count up to 11:43. So anything after this should be, I'm going to disregard it. I'm giving you guys too much time, actually. This is a very simple question. Unfortunately, not a lot of people actually. So I'm not sure why people don't like give me the correct answer. Like I think it's about 30% of people gave me the right answer. Maybe it's because I didn't explain this too well, or maybe you guys are not just following me. I'm not sure. Like maybe I'm not as effective as I hope to be. So this one's answer is 20. I said that the C is called, like C, you need C for each time step, right? And each C calls this 4 times. Like here, it's right here, it's four times. And there are 5 words, 1, 2, 3, 4, 5. So it's 5 times 4, it's 20. Yeah, I don't think I can make this question any easier than this. Otherwise, I'm just going to, it's like the same as I might as well just give you guys everybody 0.1 if I'm going to make this any easier than this. So like this quiz 1 and quiz 2 will be kind of like the norm of the difficulty of the forthcoming quizzes in the future. So okay, so the last one is just simple attention example. So as I said, that attention can be used as a way of interpretation or explanation. So what happens is I think it's English to French. So let's go that way. So there's English here, there's French here. So English is all when it all went into the encoder. So it's like H1, H2, all the way to like H something, right? And then based on that, so the encoder is done. So now decoder is trying to predict one word at a time. So there should be a start token somewhere that we can see. And then from that, la is predicted. And feeding the la to the next input, destruction is predicted. DL, equipment, signi, fi, la, siri, whatever. So that's it. So what happens is that each time a French word is predicted at each, like this will be S1, this will be S2, S3, S4, each time, a context vector is formed, and the way context vector is formed is a weight sum of all the English words or English hidden vectors, actually, not English words, the H1s to H like 15. And the strength is reflected as a brightness of the cell of the patch. So this should have like alpha 1, alpha 2, alpha 3, all the way to alpha 15. And on that, another alpha 1, alpha 2, alpha 3, all the way to alpha 15. alpha 1 all the way again, like each time. So in predicting, for example, predicting destruction, the French word destruction, the strongest strength, the alpha, was given to the first hidden vector h1 because it's the same word probably, So destruction, that's good. And like Syria in French is like Syria, I guess. Syria, when predicting the word Syria, the weighted sum was such as that this was the brightest. This was the one that this alpha was the one that had the largest value, which happens to be Syria, Interestingly. And let's see. And yeah, I guess like plus, I'm not sure why plus has two like like equal weighted from longer produced, but I don't speak French, so I don't know. But anyway, you can see that you by looking at this, you can see that okay, so the English French translation is working probably okay because like this like series, so it understands the word between the two. And interestingly, because they're all Latin-based language, you can see a diagonal line like forming here. But if it was between like English and Korean, then it would be like going all the way around because the sequence of the structure of the words, the structure of the sentence is very much different between English and French. English and Korean. And note that this was all learned on its own. People didn't like, it's not the researcher or developer that said equipment is equipment and destruction is nobody explicitly injected this information. It's just by going through all tons of parallel corpus between English and French, the model just learned to understand the relationship between French words and English words, and that's it. And that was all encoded into this attention function. So the model is kind of picking up the linguistic signal, interestingly. Question, can you explain why EOS token is also? Exactly, you need to figure out when to terminate the output. Otherwise, you'll go on forever. So I guess Cha-Jun understood how the sequence-to-sequence model works in practice. And yeah, that is the correct answer. It only ends when EOS is generated. Plus means no longer in this context. Oh, I guess Aldo is from France, I guess. Plus is no longer. Oh, no longer. Then it should be plus no longer. It should be not this, but maybe this. I mean, it's not perfect. You can see that it's not perfect, basically, because like I'm not sure why ni is can or lies. I mean, it makes sense most of the time. It makes sense, but it's not it's RNN is not a professional English French translator. It is bound to make mistake, and it probably understands language in a different manner than people do. So it doesn't always correspond to our human intuition, but it's still like a nice way of knowing what's happening inside. And you can still do this in Transformer. It's just that Transformer has like too many layers. This is just one RNN, like one RNN for encoder, one RNN for decoder. But in ChatGPT, for example, ChatGPT 3.5 uses 96 transformer layers. So there's 96 attention distributions all spread around, and it's really hard to understand what's happening with 96 attention maps. So yeah, we'll get to that. Actually, though, so tomorrow, next week is Transformer. I think the week after next week is BERT and GPT. So we'll talk about that in 2 weeks later. Okay, so this is the end of the class today. Oh, we've finished 12 o'clock sharp. So thank you for staying around. And if you have questions, you can stick around, I guess. Plus can be both more or no more, depending on, it must be hard for models to see that. Sure, yeah, I guess so. I mean, it's all depending on the context, and unless you use like very like heavy transformer, RNN is definitely not capable enough to grasp the like subtle context, subtle nuances, because it hasn't seen as many training samples as Transformer, first of all, and it cannot actually digest digest as many training samples as Transformer anyway. And question, is there if you have places to go, you can leave. The class is over now. I'm just staying here for the question, the people who have questions. Plus Q1. Is there an intuitive reason why RNNs or CNNs sometimes perform better than transformer on small data sets in certain domains, or is it a result that has emerged from heuristic experiment across? No, it's not heuristic. As I said, it's based on inductive bias. I told you guys in the CNN section, did I? I'm not really sure. CNN is based on kernels, a 3x3 kernel. It moves you move the kernels around to gather the information in your two-dimensional image, right? And which means that you can only look at 3 pixels by 3 pixels at a time. And anything outside these 3x3, you need to look it up. You need to look, the model attends to it, for example, or the model views it in the next layer. In the next layer, you've seen the receptive field growing larger and larger, right? So only by going to the next layer, the model is able to see pixels that is outside the kernel, which means that there's a very strong inductive bias that CNN, or the image handler, image encoder, it can work well with only by looking at immediate pixels in each layer. This is a very strong assumption. Like, the only thing that's important is the one that is immediately your neighbor. That is a strong assumption. So CNN has a strong assumption like that. RNN also has a strong assumption. RNN has a strong assumption, which is that your data will have a sequence, will have an order. So that is why I'm going to run a for loop over encoding each token or each input from the sequence. That is a strong assumption. So those assumptions make the function very narrow in terms of what it can learn. You know, if you give, for example, if you give image to an RNN, it wouldn't be able to learn very well because it makes a different assumption. And if you give sequence to a CNN, it wouldn't be as effective as RNN because it has a different assumption. For example, like that, like each model was designed to digest certain types of information, certain types of signals or data. So that is why CNNs work well with images, RNNs work with sequences, but transformer doesn't have any inductive bias. It doesn't have any assumption that only the vicinity will be important, or your input will have an order of tokens. It doesn't make any assumption at all. It's a set encoder, basically. We'll get to that next week. It's a set. You have a set of things, set of tokens, or set of pixels, or set of elements, or set of sensor readings, whatever. You have just set, and then you dump that into transformer, and then the transformer will have no assumption. We'll just try to calculate the correlation between every single sample to every single token to all the other tokens. It's basically a square. It's like a quadratic computation. We'll get to that. So the less the assumption you have in designing your model, it means that it can learn more things, but it means that therefore you need to put more data into it. But CNNs and RNNs, they have certain very strong assumptions. So because that the design is, like, you know, it's directed in a very specific manner. The function, the capability, or the function that the RNNs or CNNs can learn is very specific. That is why you can give a rather small amount of data, and then it still performs well. So that was question from Q1. In attention model, C views all alphas, and alpha 1 views again all the... No, alpha 1 views only H1. C takes all the alphas. Actually, C is a weighted sum of all the H's based using the alpha weights, and each alpha I is generated based on each HI. So alpha I doesn't look at any other H's. Yung one. Isn't EOS token generated from student token and attention? But in calling attention function number calculate, you also consider EOS token, which has come from... What do you mean? But in calling attention function number calculate, you also consider the EOS token. Oh, okay, I see that. Doesn't really matter, because then you can think about having a start token that needs to call. So needs to come from somewhere. I comes from start. So start token will actually need to call attention function anyway. So it doesn't matter whether you consider start or EOS in your decoder. It's 20, and regardless. Inductive bias assumption can be adjusted to small data set, but large amount of data cannot be adjusted. That assumption. Thank you. Okay, that's good. All right. Okay, cool. So any more question? Okay, so hopefully, I guess a lot of people already left. So for those of you who are still around, 55 people, hopefully you completely understood how attention works, because transformer is all about attention. It doesn't have any for loops at all. It's purely based on assumption, based on attention calculation, and that is the beauty of a transformer. So we'll get to that next week. All right, thank you guys. I'll see you guys next week. Bye bye. Thank you. 네, 감사합니다. All right, thank you. Bye bye. 감사합니다.